Hi, this is an example problem from chapter 22. It has to do with self-induction. Pause for a moment and read the question. So this example is a little bit different than the previous ones we've seen because the magnetic flux is actually produced by the circuit itself, right? It's its own magnetic field that's changing, which causes the circuit to respond to oppose that change. So you can see a picture here. We've got an AC generator, which causes current to flow and oscillate back and forth different directions. And as a result, we've got this wrap of wire here. This looks kind of like a solenoid. And it is a solenoid, it says. As the current flows, we can go ahead and use our right-hand rule or our alternate right-hand rule to determine that, well, if the current is coming over the top here like this, then wrap your fingers around the direction of the current. Your thumb points in this direction. That's going to be the North Pole. And so right now you have a flux that is passing through the loop, and it's going out in that direction. However, as the current oscillates back and forth, changing directions here, right? We're going to get the flux is going to switch back and forth this way, then back to this way, etc. The magnetic field, of course, right? These are changing directions back and forth, causing the flux to go in opposite directions. And that's going to cause the circuit itself to try to oppose that. The result is that it's always going to oppose changes in the current. It can't stop the current, but it generates a EMF that opposes a change, and we'll calculate how that works here. So to start, we're going to do what we always do. We want to calculate the induced EMF. We're going to use Faraday's law, which is going to be minus N times delta phi over delta T. Now for this one, let's just focus on the magnitude of the induced EMF, so we can get rid of this. And we're going to go ahead and figure this out. So the first thing we need to know is that the magnetic field is produced itself by the solenoid. Remember that the equation for the constant magnetic field through the solenoid, this guy here, it's equal to mu naught times the current in the solenoid times N. N is the number of loops per unit length, right? So N is this. Total number of loops, capital N, divided by the length of the solenoid. We're going to go ahead and put that into our equation now. So in this case, N here, we can rewrite this N if we want as NL. Let's just do that in the equation. So for Faraday's law, our N becomes NL. And then we're going to have delta phi, which means delta B times A times cosine of phi, all divided by delta T. Okay, so now I want to focus on the things that are changing here. BA cosine phi. Well, the normal line to the loop is straight through the center, and that's the same direction as the magnetic field side the loop. And so we can go ahead and say that this is a direction of the normal line, and it's also the direction of the B field. So our angle phi here is equal to 0. They point in the same direction. That's 0, and cosine of 0 is 1. That takes care of that. Also, the area, right? The cross-sectional area of the loop, whatever this is here, this area, that's going to be constant as well. We can factor that out. By the way, that metal block you see in there, that's a chunk of iron, an iron core, to amplify the induced magnetic field. So factoring out the area that doesn't change, we are just left with delta B over delta T. And finally, we're going to put in the equation for the magnetic field for delta B. So this gives us a NLA delta B. That's going to be mu 0 I n from this equation. And finally, all over delta t still, if I want to go ahead and factor out the other things that aren't changing here, well, this is a constant, and so is that. I can factor those out as well from the delta. And we're going to end up with this. Get a mu naught. We're going to get a L. We've got two n's now, factoring that other one out. And then we're going to have an A. We're left with delta I, the change in the current, divided by delta T. And that is pretty much it. We just need to put our numbers in at this point. All right, well, I've thrown in all the numbers here, and so we can see, right, here's the length. Here is the cross-sectional area. Here is the number of turns. Here is the change in the current, so your final minus your initial. And what we have left then on the bottom is just the time interval, 0.2 milliseconds, right? And of course, this is just a constant magnetic permeability, which you can look up. Putting all those things into the calculator gives us an answer. The EMF, it's going to be equal to 1.60 times 10 to the minus third. Now we got a whole bunch of units here, but we're in SI units. We know what the EMF is going to be. It's like a battery, so it's volts. And that is our answer there. Now for this problem, it's interesting that that voltage, it always opposes the direction of the current. So if the current is going in the direction it shows right now, it's as if we have another little battery in there that's going to go like this. Plus minus to oppose the generator. When the generator reverses, that induced EMF is also going to reverse direction. And so in this way, we can see how this solenoid, it opposes change in the current. We actually call this an inductor. And it's interesting that we can use inductors for circuits. They're effective, especially in an AC circuit like this where the current is always changing. They don't do anything when you have a circuit where the current is constant, because then the magnetic field doesn't change. There's no magnetic flux that changes, and nature has nothing to oppose if the magnetic flux is not changing. Just one last thing to point out. This is just a geometric property of the solenoid, but in general, we can always write the EMF for any object like this. We call it an inductor. Typically it's a solenoid. We can write this EMF, that L takes the place of all those units. For a solenoid, that's what it's equal to. For other shapes, it's different, but it's always geometric. And then it's going to be equal to the change in the current over time. And that's the equation for inductance. I'm just showing this because we're going to look at that a little bit next week. And if we're going to get rid of the absolute values, we've got a minus sign because that shows us that the induced EMF always opposes the change in current.